Hi, good evening everybody. Thanks for sticking around for my talk about common API security pitfalls. Before we get started, I want to set the scene a bit. What do we mean with an API? What are we talking about? Well, in general, or what this talk is about, it's going to be about web APIs. So you have a browser who's going to load an application from somewhere, and essentially that application is going to access an API in the backend. And it's going to be fetching data from that API. In this case, it's going to fetch some JSON data, or send some JSON data and get potentially something in return after authenticating. Of course, this is the web application example. The same holds for mobile applications and native applications that use an API. So essentially what we're going to cover here is going to be valid for all kinds of types of applications, but I'm going to focus on the website. So some of the potential pitfalls will be related to web applications. Why API security? Why is API security so important? Well, actually, in the OWASP top 10, they're creating a new one for 2007. And in the first release candidate, there was a separate issue or separate item for underprotected APIs. And well, it actually didn't make it into the second round or the second release candidate, so it's removed now. But what's important to know is, or at least what I believe, is that APIs don't all of a sudden suffer from new kinds of vulnerabilities. We see the same kind of problems that we've known for quite a while, and we see them reappear in APIs. We see a lot of problems that we're familiar with, and they come back in the same form or in a different form, causing all kinds of problems or security issues for your APIs. So we're going to talk about these things. I have a set of pitfalls I want to go through, and I want to offer you a look into the problem behind the scenes and how you can solve it. First, a quick word about myself. I'm actually here to help you build more secure applications. In my day job, I give trainings on security, on software security and web security. So that's kind of what I do. I also built an online course about web security, which is the Web Security Fundamentals course. So if you're interested in that, definitely check it out. It's still running until the end of December. And I'm organizing SecOpDev next year, which is a week-long course on security taught by international experts. Next year, we have the security manager for .NET at Microsoft is going to teach a few lessons on .NET security. So if you're working on .NET, that's definitely something you don't want to miss. And there's plenty of other topics there as well. But back to APIs and API security. I'm going to start with a very simple one. Normally, I would ask this as a question, but you can imagine in a room with a couple of hundred people, it's not going to work well with people shouting answers from all the way in the back. So I'm going to give you the answer for free. But first, the question. What's the most important security thing you can do for your API? HTTPS, of course. This is the baseline security requirement for anything that you're building today. And it's really, really, really important. So I'm going to underline it. And the reason it's so important is because everything we're going to talk about today actually builds on top of HTTPS. If you don't have basic network layer security, using TLS, of course, then actually all you're doing on top of that is going to be vulnerable by default. It's not that it doesn't matter that you're protecting against other vulnerabilities as well. It means that if an attacker is close to the victim, there will always be ways he can break your security that is currently in place. So HTTPS is absolutely the baseline. It used to be hard to deploy HTTPS. It used to be resource hungry, used to be expensive. Today, well, all of those excuses are no longer valid. So performance-wise, there is almost no overhead. And if you use HTTPS to bootstrap HTTP2, then the overhead is even less than a normal HTTP connection. And Let's Encrypt is a free and automated CA offering certificates for everybody. So the main arguments for not using HTTPS are gone. So you should be doing this. A few things, if you need to do this for your API, it's actually quite useful to know that you can actually simply offer your API over HTTPS. You're not a web application. Your API will be accessed from within another application directly, so you don't need to support the redirect from HTTP to HTTPS. Of course, if you have legacy applications depending on that, don't disable that tomorrow. Otherwise, you're going to run into all kinds of trouble there. And once you've done that, the second important thing you should be doing is enabling strict transport security. And strict transport security is a browser security mechanism that you can enable, and you can tell the browser for the next period of time, I don't want you to send any HTTP requests to my endpoint. I want you to use HTTPS by default. Even if somebody types HTTP or tries to fetch an HTTP resource, don't do it. Use HTTPS. You configure that with a header, and that's all I'm going to say about HTTPS. Configure that with the header shown below, and you give it a max age. And the max age is in seconds, so in this case it's for a year. If your browser sees this for the next year, he will never send you an HTTP request again. He will use HTTPS by default. And that's a very, very important thing to start with. and to use as a baseline for security. It brings me to the first security pitfall of this presentation. So essentially, allowing your API to be accessed over HTTP is something that you shouldn't be doing. That's going to cause you problems. So if you're still doing that, phase it out and deploy HTTPS and enable HSTS as well. I have 11 more security pitfalls. So as you can imagine, in 45 minutes, it's going to be quite a content-packed presentation. I hope you don't mind. I know it's late, and I'm holding you away from beer and fries, apparently, but try to bear with me. As you can imagine, 11 issues. I'm not going to go into each of these issues in a lot of detail. I'm going to sketch the context of the problem, the root cause, and I'm going to sketch the solution that you can deploy or enable to prevent that kind of vulnerability. If you have any more questions, there's often references at the bottom of the slide, so you can look it up, or you can also come to me after the talk, and we can discuss about the questions you have. All right, let's move on to the next issue. I have an example. This is a story from Facebook. Somebody found a vulnerability in Facebook, API related, of course, and he actually got quite a big bug bounty for that. And the problem he found was that if you reset the password of an account on Facebook, then Facebook sends you a 6-digit code. You have to enter that code to confirm your identity. Code is sent through email or a cell phone or whatever, and then you can access your account again. And he discovered that there was a test version of Facebook accessible publicly, where there was no rate limit on the amounts of tries that you had for entering that code. So you could simply brute force the 6-digit code for any account, and using that, he could take over the account. Of course, Facebook was quite quick to fix that. It was already fixed in the main Facebook version, by the way. Just to show you that one of the pitfalls is allowing unlimited access to an API. Regardless of what kind of API you're offering, you should always limit the number of requests that a certain application or a certain person or whatever can make to that API. The obvious case is denial of service. If you limit that, then you're limiting the potential for denial of service attack. But the second case is brute forcing certain things, brute forcing authentication. Trying to enumerate a lot of resources, extract a lot of information from an API. Even though it's legitimate access, you probably don't want someone extracting gigabytes of information through your API. There's a lot of strategies you can use. There's no one solution for every application. So you have rate limiting based on connection properties, for example, IP addresses, also per user account or per API key. So Twitter does rate limiting based on API keys. So every application has a different API key, and based on that, they can decide to limit your access to the API. But you can also do it per user account or even per region if you have a lot of spread out customers, for example. And actually, a funny thing is, a lot of APIs already offer rate limiting in another form. They use it as a business driver to distinguish between subscriber models. So you all know the subscriber models where you pay a little bit of money and you get this amount of access per month and so on. Of course, that kind of rate limiting is in a much larger time window and is not very useful to prevent these brute force or extraction attacks. So set sensible limits on your rate limiting. How do you do that practically in an API? Well, actually, there is a status code for that. You can use 429, too many requests, and essentially you can also include a retry after header. So you can inform the client that it should stay away for that amount of seconds, and then it can try again because the limit will be lifted. And that's very useful to handle in your client-side part of the application where you can actually inform the user of the limit being imposed and the wait time that will incur. Second security pitfall, don't forget to rate limit your APIs. May seem silly for your application, but try to do this and get this right, and it will save you a lot of trouble if something goes wrong anyway. All right, a bit related to rate limiting is the next one. Again, an example from a couple of months ago from T-Mobile. You may have heard about this. Using a phone number, you could access account data on their API, essentially. So they exposed a lot of information accessible by knowledge of the phone number. And what's actually going on there is a problem we know as insecure direct object references. So the phone number is essentially an identifier, and they use that identifier to look up account information. By itself, there's nothing wrong with that. You do that in your applications probably every day. So it kind of makes sense to do it like that. However, the problem is, they never checked whether the person accessing that account information actually should be able to see that information. There was authorization missing on that call, and because of that, you could simply access any account that you have the phone number of. So you can imagine if there's no rate limit and you have a bug like this, you're going to run in trouble, like T-Mobile did with this bug here. Insecure direct object references seems like a silly problem to have. Like who would build an application that doesn't check whether someone is the owner of a certain resource? And at first sight, they seem trivial, but I'm going to show you an example. This is from a tutorial I found in 2 minutes of Googling. Well, actually 30 seconds, I think. It's building a RESTful API in 10 minutes. So 10 minutes is quite short, so you can imagine that they're going to skip a few steps. And here they skipped authorization altogether. So essentially you can see this is a function to get something by ID, and it returns the object by ID. If you deploy this in a real application, if the user is not allowed to see all to-dos, you're in trouble. So you can imagine a project starting out with a very simple proof of concept that does something like this, and then it starts growing. You add authentication, of course, afterwards. You add an authentication check, and you simply forget to add the authorization check as well. And that's how these kind of vulnerabilities are easy to make. This is reading information. If you think about deleting or updating or writing information and you have the same vulnerability, this may be quite problematic as well. So these text slides contain some of the stuff I already mentioned. It's for your reference later in case you don't remember all of it after too many beers this evening. So use them. The slides are online on my Twitter account, so you can easily find them and look at them later, tomorrow, next week, whenever you're doing this stuff. So the real problem is that many APIs do authentication checks, but they forget to do the authorization checks to check who is actually accessing this information. And doing that is the only proper defense against this kind of vulnerability. So you should check the owner of the resource. There's a complementary technique. You can also use non-predictable identifiers. If you do that, then it's hard to enumerate a large set of objects because you can't guess what the next identifier is going to be. So you can use a UID for that, for example. That's not going to be predictable. It's long enough to be, well, to have a large space of options, and it makes these enumeration attacks very impractical. Don't use this as the only defense. It's not going to be sufficient, but it is a good complementary technique to use. Brings us to this conclusion. So insecure direct object references are probably a very bad idea in your API, and you should implement proper authorization there. So authorization, there's going to be a lot of issues related to authorization, figuring out whether something is allowed or not, and preventing unauthorized access. So the next part is we have to check authorization, but how do we know who is requesting access to this resource? What to do with sessions, which we shouldn't use in a RESTful API, of course. So how do we deal with that? Well, let's take a trip down memory lane. This represents web applications that we used to build 10, 15 years ago. So you have a server, you have some clients, and you have sessions stored on the server side. This is how everybody built their own first PHP application or whatever. Of course, things have changed a bit. We started deploying more and more servers. And as you all know, session management, when you do it like that, is going to be painful. If you want to spin up more versions of your backend, if you have sticky server-side sessions, you're in trouble. You need sticky sessions, or you need session replication, or something like that. And that's going to make your life difficult. So what we decided to do instead is we put that information on the client. And we have a stateless backend, which is awesome. Need more power on the backend? Just spin up new services. They're stateless anyway. Nobody cares. You can scale every way you want. Of course, it's a very small change if I do it on a picture, on a drawing. It's a small change in your architecture as well. It's actually not that big of an impact. But what we're doing here is we're putting data on the client. And storing data on the client is one thing, but we're getting it back from the client, and we're going to use that to make authorization decisions. So you kind of see where I'm going with this, right? So server-side sessions, you had an object on the server, the object remained on the server, and all you shared with the client was the identifier. So the data in that object could never ever be touched by a malicious client. There was no way to modify that data unless you controlled the server. All you could do was steal an identifier or guess an identifier, but that's about it. When you store data like that, authorization data, user data, session data, whatever, on the client, it's a whole different paradigm. Now all of a sudden a client can easily manipulate one parameter. If you store the role of the user, whether he's an administrator or not, on the client, well, the first thing an attacker is going to do is try to set a no to yes, to true, the false to true, or the no to yes, and see what happens. And I kid you not, there are applications that actually give you administrator access when they see that flag. So yes, it happens in practice. What should you do against this? Well, the solution is, again, not too difficult, but you need to make sure that it's in place. And the solution is mandatory integrity checks. Should check the integrity of the data that you get back to make sure that nobody has been messing with that data. And if you detect that somebody has been messing with the data, you can already know that something fishy is going on, and you can preemptively block them or send them to a harmless version of the site instead. Optionally, you can also deploy confidentiality. You can encrypt the data you store on a client. And that seems a bit overkill for simple user-related information, but it's very useful if you store, for example, healthcare information on the client. Depends on the kind of application, of course. If you store that on the client, then you actually might want to consider to encrypt the data just to be sure that it cannot be stolen from the device. Pitfall, mishandling client-side session data. So essentially, what we're doing there is we're storing data on the client. I call this session data, but we're going to come back to that, what that means in a bit. And essentially, trusting that it will be fine. And that's not going to end well for you. So you have to ensure integrity for one, and if you want, confidentiality as well. That's all fine, but how do we do that? Well, you can start thinking about your own crazy way of doing that. Maybe it works, maybe it doesn't. If you want to be a bit more standards compliant, you can use JSON Web Tokens or JWT tokens. There's plenty of other ways as well, but I'm going to only talk about JSON Web Tokens for this talk, because I believe that many people actually use them. I didn't expect to be able to see you with all the lights in my eyes, but it's quite okay in this room. So who here uses JWT tokens? Yes, exactly. That's why I'm going to talk about this thing. For those who don't use JWT tokens and have no idea what I'm talking about, the thing on the left, the blob of data, that's a JWT token. It's actually base64 encoded, and if you would decode it, you get the 3 parts on the right. And the interesting part is the purple one, the payload. In the payload, you can store data. Claims about anything, essentially. They call it claims, and it is about the user in this case. It can be about anything. You see 2 other parts as well. The red part, we're not going to go into that at the moment, but the blue part is essentially the signature of the payload. So the signature generated by the server, and that signature, the server will be able to check that when he gets the token back from the client, and you will know whether the payload has been tampered with or not. So the whole idea is that you create such a token, you add a signature, you send it to the client, and then whenever it comes back, you first verify whether it's still the same token, whether it's valid, the integrity is not violated. And only then you rely on the data being stored in there, and you can take it from there. So keep in mind that even though you couldn't read what was in the token, it's base64 encoded. And base64 encoding is no encryption, it's simply a transformation, so anybody can decode that and see what's in there. That's why potentially you need confidentiality if that matters for your application. The JWT specs, by default, they generate signatures. So almost every library out there offers functions to generate a signature of a certain payload and attach it to the token, creating the one we saw in a bit ago. Of course, when the signature is valid, the token has not been manipulated, so that's a very good thing. One of the drawbacks with this approach is that many libraries offer decode functions that do not check the integrity of the token. Meaning that if you, by accident, use the wrong function, you're getting the data, but no integrity checking is happening. So essentially, your code looks fine, your application works as expected, but if somebody comes around and manipulates the payload, your application will not detect that. And that's a problem. And a second problem is that simply decoding instead of verifying the integrity is easier. So there's going to be people that do it wrong. Code snippets, taken from one of the most popular JWT libraries for Java. So the top example shows you how to verify the integrity and get the data out. As you can see, the second one only decodes, but it's a lot easier. So if you're in a hurry, or if you simply find 2 code snippets and you have no idea what integrity checking means or signature checking, then it's very tempting to use the second because, hey, it's simpler. Less lines of code, less maintenance, and easy to read. If you do it the second way, you're going to be in trouble. Unfortunately, I believe, well, in my opinion, that function should not be called decode, but should be bypass security or insecure decode or whatever, just to give you a trigger like, hey, what am I doing? There's valid use for that. If you want to do that on the client where you don't care about integrity, then sure, you can use that function, but otherwise you should not be using that. Somebody starts to be scared, it's okay to leave to fix their application. I totally endorse that. So JWT tokens, whenever you use them, you should check the integrity of the tokens. Very, very, very important. All right, so JOT tokens and signatures. There are actually two ways of generating a signature for a JOT token. I hope I'm not surprising anybody, but chances are that some people have no idea what I'm talking about. Let me give you an overview of the two ways. The one we saw so far is signing with a shared secret. So essentially what happens there is if you have the payload data and you send it through the library and out comes this very colorful JOT token. I'm not sure why this is the logo of the JOT library or JOT token thingy, but well, it's there, so let's use it. So what's happening here is you have a shared secret and you give that as input. And with that input, the server or the library generates a signature and attaches it to the token. And if you want to verify that token when you get it back from the client, the same thing happens. So you call the library, you give it the secret, and the library will regenerate the signature on the payload and compare it to the given signature and see whether it matches. The security properties of this setup mean that anybody who has that key will be able to verify signatures, great, but also generate signatures. So that's something to remember. This key is supposed to be secret. And it's the same key for both operations. Second mode of operation is using a public-private key pair. And essentially what happens there is if you, again, want to generate a signature, you use a private key as input. So far, it sounds the same. However, if you want to verify a signature, you can use the public key as input. Well, not can, you have to use the public key as input. Very, very big difference. Well, private and public key, the words kind of indicate the meaning. A private key is supposed to be private. It's something that only you or your application should know. And a public key is something that everybody can know. And the benefits of this scheme is that you can, in the second one, you can easily allow someone else to verify the integrity of your tokens without compromising your secret. And the problem is that the default mode of operation is the left one. Because in a single application, you can easily use your own shared secret, and if you don't have to share it with anyone else, nobody cares. Just keep it to yourself and do whatever you need to do. It's very easy to set it up, very easy to work with. However, if you have that set up and you're not aware of the second one, and you want to start sharing your tokens with other people, it might be that you think that you have to share that secret, and you start doing that. And that exposes you to someone else generating JOT tokens that seem to be valid, even though they are controlled by the attacker. And again, this happens in practice. So one of the benefits of doing it like this, the shared secret is for within your own trust boundary, and if you have to cross that, you need to use the public-private key pair. So never ever share your shared secret to anyone else, not even your own client application. If you share it with your client so that it can also access the JOT token and verify the integrity, then you're leaking that token. If it's a web application, anyone can extract it, same for a mobile application. So even in that case, use the public-private key option, and you'll be good to go. This is, by the way, the public-private key option is how OpenID Connect uses JOT tokens. So if you log in with Google, social login on a website, it's going to use OpenID Connect, it's going to issue a JOT token, and it's going to be signed with the private key of Google, and the application you're logging into should verify it with the public key of Google. And that's essentially why these things work quite well. So depending on the scenario, each of these schemes has a very good use case, so make sure that you're using the right one and you're not mistakenly sharing your secret with someone else. Everybody good so far? All right. So we have identity information. Now we have a JOT token coming in to the API. That sounds about right. So back to my very simplistic drawing of a web application. Essentially what happens is we get this information to our API. Awesome. Of course, in a real system, you're probably not going to have this one block, but you're going to have a lot of different blocks. And often, these different blocks work just like this. So one call comes in to the big gateway API, and then it starts doing all kinds of things on internal systems. And even if you don't have separate servers for this, think about your monolithic web application from maybe today or a couple of years ago, whatever. All of these systems work in a very similar way. You have a gateway, you have a facade where things come in, and you authorize it, and then stuff happens in the system. And the real problem here is that you're not propagating identity information. So these internal services have no idea what they're doing and for whom they're doing it. They simply know that there's a call coming from the gateway to do something. So essentially what you should be doing is you should be making sure that all of these services have the proper information to make authorization decisions, that they have the proper information to make a useful audit trail. The services on the right, they should be able to log that they're doing a certain action for a certain user. And if they're able to do that, then you have meaningful audit logs where you can actually trace back what happened in case of an incident. And if you only have that on your entry point, then you're going to be in a lot of trouble figuring out what exactly happened, as we see in a lot of common data breach examples that we see today in the news. One example of where this really ties together is OpenID Connect. I mentioned this before. They use a JOT token. This is an example from one of the explanations of how OpenID Connect works. And essentially, you see a lot of interesting things in this example. So you see identity information about the user. This token could have been issued by Google, for example. When you log in with your Google account, they could have sent a JOT token containing all of this information about your user account. It contains an expiration date, things like that. It contains roles, which is useful for authorization decisions. And what's also very, very cool and often unknown is that the ACR property that you see there refers to the level of authentication used by the user. So in this case, it indicates that the user logged in with two-factor authentication. And that information allows one of your internal services that maybe wants to perform a very sensitive operation to determine how the user authenticated. And if the user used a strong mechanism, such as two-factor, then it can decide to do this operation. And if the user simply logged in with a username and a password, or was logged in from a mobile device, the application can decide to request additional information or additional authentication before performing that sensitive operation. Very, very useful, very powerful, and ties in nicely with OpenID Connect. So propagating identity information is a very important thing. It's something that we see being, well, not done wrong, but missing in a lot of applications, even traditional applications that don't use different services internally. And that's something that really, really needs to be there. All right, I'm about halfway through, so that's good. Time-wise, we're doing fine. So we have time for a little poll. The next topic is going to be how you transport authorization information from the client to the server, to the API. Who here is using cookies to do it? Come on, don't be afraid, it's okay. It's a web application, you can use cookies. Okay, so 10 people apparently. Who here is using the authorization header? Okay, a bit more. Who here is not sending any authorization information at all? All right, so most of you are actually using the authorization header. That's kind of expected. The next topic, I don't have a strong opinion about the next topic. I'm going to lay out both systems. I'm going to lay out the advantages and disadvantages, and then you can make up your mind about which one may be better. They both have problems. Let's call it like that. So first, cookies. Cookies have been around for a while, and they're an absolute mess. This is virtually well known, but they are very compatible with the web. So if you're running in a browser, if your application is running in a browser, then cookies will be handled automatically by the browser. You don't have to do a thing for that, which is awesome. Cookies will be present on all requests, including a request generated by the DOM. So if you have an image tag fetching an image, and there's a cookie for that domain, the cookie will be present on the call to fetch that image. Same for JavaScript, CSS files, things like that. And even cooler, if you use modern things like server-sent events or WebSockets or CORS, cookies are very compatible with that, because the browser attaches them automatically. Of course, as you probably all know from now or from the past, cookies are a bit difficult to get secure. So you have cookie security flags like HTTP only and secure that you need to enable if your framework supports that. You have cookie prefixes nowadays, so you can add a prefix to the name of the cookie, and that's going to enable additional security behavior in the browser. But again, you need to be able to modify the name of the cookie, which is something that not a lot of frameworks actually allow you to do. And of course, if you use cookies, you have to deal with cross-site request forgery, or CSRF, which I'm going to talk about in a bit. Also, maybe the most important disadvantage, cookies are a nightmare to support in non-web applications. If you have a mobile application and you need to figure out how the set cookie header works and the cookie header, that's going to be quite painful and not fun to deal with. That's cookies. Custom headers, like the authorization header. They are actually quite straightforward to use. So you simply add a header and you're done. But the browser doesn't do it automatically, so you need to do it. Your application will need to actually take care of that itself. And that means fetching the value that needs to be sent first from a response, storing it somewhere, and attaching it to the header. I have a lot of content on how to do that on the client and what the advantages and disadvantages are, but I'm not going to go into that here. That's something for the discussion afterwards if you want to. The second problem is that the browser doesn't attach this header automatically to requests coming from DOM elements. So what we see a lot is applications wanting to enforce access control on JavaScript files, on CSS files, on images, but it's simply not possible because there's no header there. So you need to use cookies anyway as an alternative mechanism, which makes it messy again. And if you use things like server-sent events or WebSockets, then things get a bit more difficult with the authorization header as well. And if you really look at what's going on, surprising this is actually surprisingly difficult, because you have to decide where you store this information on the client side then. You have to attach it to outgoing requests, and you're very likely to mess that up, no offense. The good news though is there's no CSRF if you use the authorization header, so we're good on that regard. Also, if you have a non-web application, like a mobile application or a native application, this mechanism is also quite easy to use. I may have offended you when I said that you might mess it up sending the request. I'm going to give you one example. It's an Angular example of how easy it is to actually screw this up. This is, again, from a tutorial. This is how most applications in Angular, this is an Angular 1 example, attach the token to the authorization header. So essentially what's happening here is you have fetch the token from local storage, and then you add a header, and you add a bearer value, and you add a token. And that's it, you're done. This is an interceptor. This will happen on every outgoing request made from within Angular application. Sounds good, right? Well, the drawback with this is if it works perfectly fine if you use your own API as a backend. But the moment you start using a third-party API running on a different origin, this piece of code will attach the token to that outgoing request as well. So all of a sudden, if you fetch anything from within your Angular application from another origin, essentially, you're starting to leak your authorization token or your whatever token, in this case, on those requests as well. So you actually need to check where the request is going and whether you want to attach that to the outgoing request. And that's one example of how these things are a bit more trickier than they seem at first sight. So don't minimize the impact of the transport mechanism. Sure, cookies have a lot of disadvantages, and I'm not advocating the use of cookies. But on the other side, if you do it yourself with the authorization header, make sure that you do it securely. Make sure that you know what's happening there and that you figure out whether you are vulnerable in that regard. So next up is cross-site request forgery. Most of you may want to take a 3-minute nap here, because it doesn't apply at all if you use the authorization header, so it's only valid if you use cookies. So let me give you a very quick overview of what it is, and I'll tell you when to wake up if you want to doze off there for a moment. So what is CSRF? Let me first give you a traditional example of cross-site request forgery in a normal web application. So I have a quick scenario to run you through it. You have one application that you want to visit, and after you log in, you get a cookie and with your session information. And essentially what happens is when you make another call, the browser will automatically attach the cookie to an outgoing request. And that's how the server knows who we are and how it can fetch our messages. Now what happens in a cross-site request forgery attack is that another site, in this case with funny cat pictures, does that call for you. So in this case, it's going to ask the backend to post a message in your name. And the browser is very helpful when it comes to cookies. The browser is like, I have a cookie for that. Let me attach it to the request. And the server has no idea, in a CSRF attack, he has no idea that this is coming from here, no idea that this is default behavior that's allowed on the web, and he simply processes it as if it was the real application asking for that. And that's essentially the essence of cross-site request forgery. And this used to be a big problem in traditional applications because a lot of applications did not protect against this out of the box. Many do nowadays, so that's a good thing. And that's definitely a real vulnerability. It's actually so real that criminals use it to reconfigure your home router and change the DNS settings. So essentially, they make the call from within your browser, they make the call to the router, and ask the router to change the DNS settings. Of course, they have to guess the password, but it's probably going to be admin anyway. So they make the call, change the DNS settings. From then on, they can control which sites you get to visit, which may be problematic. In this case, they used it. I'm not sure. They have used it in the past for stealing banking information and things like that. So it does have a serious impact. It exists because the browser handles cookies liberally. So essentially, every outgoing request to a domain, the browser slaps a cookie on it if he has one. And that is kind of a problem because requests may be unintentional. Many APIs are essentially unaware of this problem. Again, note if you don't use cookies that this is not a problem. So one of the problems here is that a DOM element, such as a form, can easily trigger a post request to a different origin and send you some information. And then it depends on how your API is built, what's going to happen with that. Maybe it processes form submitted data. Some APIs are very liberal in the content type they accept, and then you're going to be in trouble again. If you have put and delete methods, those are a different story. I'm going to come to that in the next issue. How do you defend against CSRF? Well, in a traditional application, you use hidden form tokens. So the idea of hidden form tokens is that you hide a token in the form, and you check when the form is submitted whether the token was there or not. And if it's there, then the application considers this to be a valid request. You can imagine that form tokens and APIs probably don't mix too well. Well, you're kind of right about that. So in an API, you can use an alternative mechanism using transparent tokens. Well, let me show you how it works. Essentially, you have the same scenario as before, but instead of getting one cookie after we log in, we get 2 cookies. And of course, the 2 cookies are sent by the browser as well. But what also happens is that the client-side application, in this case, let's say it's an Angular application, that the Angular application has to copy the value of the cookie, ABC here, to a header called XSRF token. And essentially what the server now does, it verifies whether these 2 values match. Of course, you should use something else than ABC and something random, which is a bit longer, but bear with me. So essentially when these match, the server knows that this is a legitimate call because only this application could have read the cookie that was set for that application. Of course, don't set the HTTP only flag on that CSRF cookie either. What happens if the attacker comes along? He tries to do the same thing. He sends the message, the browser attaches the cookies, of course, but the server sees that something is wrong because the server sees that there's no additional header containing the cookie because this context comes from anysite.io. It's not able to read that value, so it will not be able to add the header. And that's how you defend against CSRF. This kind of behavior is enabled by Angular by default, for example. So Angular looks for this XSRF cookie, and when it finds it, this cookie name, it automatically copies it to this header on every outgoing request to the application. So that's a very useful way of defending against these kind of things. But of course, on the web, it's never quite simple. So we need to talk about something else, cross-origin resource sharing. So CSRF used to be a big problem in traditional web applications because you could easily, well, web applications depend on form submissions and you could easily fake them from another website. In APIs, it depends on how you have built the API, which mechanism is kind of relevant. So let me walk you through it. So essentially, these kind of cross-origin requests have always been there. But the power that, or the kind of requests that they can generate are very limited. You can use an image for a get, that's very easy. You can use a form, but you only have 2 or 3 content types you can choose from. All the other content types are unavailable. You cannot set custom headers from a form. Those things are unavailable. So if you have an API supporting traditional HTTP requests, then you definitely need to worry about CSRF. These things matter for you. If you have a JSON API that only accepts things from application/JSON as a content type, then CSRF will not matter because a form will never be able to generate such a request. Very important. And why does that matter? Because once you start sending non-traditional requests, things that could never have been sent from HTML, then you fall under the protection of CORS, cross-origin resource sharing. And CORS is actually a security policy in the browser that it's meant to allow cross-origin communication without running into these boundaries of things not being allowed. And I'm going to talk about CORS in the next topic in a bit more depth. So what you need to remember here is, well, 99% of the room, if you don't use cookies, don't worry about CSRF, and you're done. If you do use cookies, you need to check how your API is accessible and what kind of things you accept. And if you accept things that can be generated from within an HTML page, then you're probably going to need to deploy some CSRF defenses on your API. All right. 11 minutes and 3 issues. We should be fine. Cross-origin resource sharing, CORS. Let me first give you an example of the basic setup for CORS, and then we're going to talk about a couple of pitfalls or things that can go wrong. So the idea behind CORS is that you have a browser and you have a server, and you load a page from one website. That page is going to do an XHR request to a different website. In this case, well, you see the code here. It's simply constructing it, setting a URL, and sending the request. That's all that happens. And essentially, that is going to trigger a request to the backend. In this case, you see that the 2 headers, well, there's actually a lot more headers, but 2 relevant headers have been added, the origin header and the cookie header. The cookie header is here because you have told the browser to use credentials. Remember when I said that cookies are compatible with CORS? Well, credentials in this sense means cookies, even though you're using the authorization header. And the second thing that's going to happen is the browser is going to add this origin header because it's a cross-origin request. The server, if he wants to allow this kind of behavior, should tell the browser, hey man, I know that this context is trying to access me. I'm going to send you permission so that you can actually allow that context to access the response. That's essentially what's going on there. And this header tells the browser that, oh, by the way, I knew that you used credentials for that, and I'm fully aware that that's allowed. And that's essentially, well, in a very brief nutshell, what CORS is about. Why this example? Well, actually, if you look at the endpoint that they're calling, this is called request API key. And what a lot of applications are doing nowadays is they use temporary keys to access an API, and you add that key with the authorization header. And the long-lived token, which can remain valid for a long period, like a week, 2 weeks, a month, is stored in a cookie, an SSO cookie or something like that. And using that cookie, they fetch API keys from the backend. And if your backend is misconfigured, if you have a problem with your CORS configuration, then anyone can request an API key from that backend, tell the browser to use credentials, the browser will send this call and give any context here access to that response containing that API key. And that is a huge problem. And that's a problem that a researcher actually observed and wrote a very interesting blog post about and gave a very interesting presentation at the conference earlier this year. And I'm going to run through 4 common misconfigurations in web applications that allow this kind of behavior, and that essentially exposes them to all kinds of attacks. So this is the culprit here, checking the origin header whether this one is allowed to access our application. If you build this yourself, then well, you may have had the idea to use the starts with or ends with methods to compare this to a whitelist of allowed origins. Hey, if this one starts starts with our value, then it should be fine, right? Well, it depends. Depends on how you have defined your whitelist. But these kind of methods allow bypass attacks. So, for example, if you check for it ends with www.example.com, somebody could generate a URL that matches that filter, even though it's not one of yours. Example, it starts with, if you simply add that and then add .evil.com behind it, then the starts with is going to match, and you are in trouble. So that's one way to bypass these CORS filters. A second way is the null origin. So a lot of applications actually allow null as a valid origin, but null can be generated by simply sandboxing the piece of code. So an attacker can easily trigger an origin header with the value null. So if you allow that, again, you're in trouble. If you only check the domain and not the origin, so if you check www.example.com but forget the HTTPS, then somebody can trigger an attack on the network which launches a request from HTTP www.example.com. And again, you will allow that, allowing anyone to access your API. And the worst offenders are those that simply reflect back the value from the origin header. Essentially, they have a wide open CORS policy by default. And this sounds absolutely crazy. Like, who would do that? Who would simply allow anyone to access anything? Well, again, I Googled for this, and I found, I'm not sure what it does, but I found a system that encourages people to configure it like this. And essentially, it says, you extract the origin from the incoming origin header, and you attach it again in the access control allow origin header. And by the way, you set the allow credentials flag to true, just in case. And if you do it like this, essentially your API is wide open for anyone to request everything they want, which is probably not what you intended. So, the almost final security pitfall Insecure course configurations are a real thing, and you should be worried about those. Check your course policies. It's not only the implementation details I mentioned here, but also allowing too much access, allowing essentially all methods for all origins. It's probably not what you want, so take the time to narrow this down. I know it's a pain to configure, but it's going to be worth it in the end. 2 more, 5 minutes. I think I'm going to make it. We'll see how it goes. I have actually one issue which I split into 2 different pitfalls. The issue is input validation. Should this be accepted by your API? Well, maybe, depends. Looks fishy, right? Well, you're probably guessing where this is going to. This is going to lead to SQL injection. So essentially, one of the things that you should be doing is you should be doing input validation. Input validation is a really important first line of defense. So essentially what we're doing there is we're validating untrusted data before we use it. Things that you should absolutely be doing, even though input validation has its limitations. That's the last one. What you should be doing is you should only accept content types that you expect. I mentioned this with accepting form data. Well, if you're a JSON API, you shouldn't be accepting anything that is not application/JSON. Just reject it. Validate data against their types. If you expect a number as input, an identifier, check whether it's actually a number. Don't allow anything else. And these sound very simple and very straightforward, but this is something that's often not done, resulting in all kinds of vulnerabilities. Also, sensible length restrictions based on the content for one, but also a strict upper limit. If you expect a long piece of text, make sure that nobody gives you a few megabytes of text, because probably your system is not going to handle that in a graceful way. So lack of input validation is the second to last security pitfall. Make sure that you have input validation in place. On to the last, but input validation also has its limitations. It targets the symptoms of a problem, but it's never going to be able to weed out the problem, to fix the problem for you. Think about the example I gave earlier. It's SQL injection. Validating your input is not going to be enough to prevent a SQL injection attack. The only defense is using parameterized queries with variable binding. And that's going to make sure that the root cause of the problem is addressed. Because input validation starts failing the moment you have complex enough input. The moment you have to allow, well, even something as silly as the name of a user, it's going to be a lot of trouble if you want to put that data in a SQL query directly. So essentially, the only way to do that is with proper secure coding practices and not with input validation. If you want an example of this, look at Google for XSS filter evasion cheat sheets. And you have a huge list of ways to evade cross-site scripting filters, because it's simply too hard to do that at input time. And a final word about this, sometimes it's not even the API's responsibility. And cross-site scripting is a perfect example. In a modern application, the API simply gives out data, JSON data. The API has no idea where it's going to be used. Is it in a mobile application? Is it in a native application? Then who cares about cross-site scripting? If it's in a web application, then of course you care about it. But here it's a responsibility of the front end. The front end is going to inject that data into the template or into the application, and there you should have the proper XSS defenses. That's, by the way, what Angular does out of the box. Because with this kind of application, Angular is the one responsible for doing that. It has the right information to do that, and it will do that out of the box for you. And that brings me to the last security pitfall. Don't rely on input validation alone. Make no mistake, input validation is absolutely very, very useful, and you should deploy it as a first line of defense, but not as the only defense, and you should not depend on input validation alone. I have 1.5 minutes left. I'm not going to give you an overview of everything we covered. It's a long list. It would be too small to read. Oh, on this screen you actually could read it, but in general it would be too small to read. So I have one important message to wrap up everything I said here. When you're building application, question everything. Think about what you're doing. Think about how it differs from what you used to do. Something simple as moving session data from one place to another can have a huge impact on your application. But also think about the validity of data. Think about integrity. Think about if you understand what you're doing. And if you don't, then you need to find, well, help online, training, of course, or anything else. And that's my final slide. I can help you, I can explain to you how to do it, but essentially it's up to you. If your guys are building the applications we use, that millions of other people use, so essentially it's up to you to build secure applications. If you want more info, you can follow me on Twitter. And the last and most important thing is, if you do something with security, please share this with other people. come to Devoxx and give a talk on how you secured your API with my input from this talk, for example. But also share on meetups within your company. This is so important, so you motivate other people to take security seriously as well. That's it for me. Thanks for being here. Thanks for staying, most of you at least. And if you have any questions, I'll be happy to answer them afterwards offline here. Thanks.